Hello, it's an everyone. My name is Christos Karras. Today I will present you the paper entitled SAF, a peer-to-peer IoT LoRa system for smart supply chain in agriculture. This is a joint work with my brother and colleague Aristeidis Karras, my colleague Georgios Drakopoulos, and the professors Dimitrios Tsolis, Phivos, Mylonas, and Spyros Sioutas. Starting off with the introduction, so the project designed and developed here is for the agricultural dairy partnership of the region of Kalavryta. So the scientific research conducted was funded by the European Union. And here we have the main goals and objectives of the project, which are the improvement of the production and the ensuring of the quality and uniqueness of the dairy products in the region of Kalavryta, the application of new methods and collaborative practices in the dairy products in the region of Kalavryta, the use of new technologies and information systems, and the traceability of a sick animal in the livestock unit. So in simple words, we can say that we monitor and manage the whole dairy product production process, starting from the first phase, which is the milk extraction process, up to the last one, which is the delivery of the product to supermarkets, to local markets, and so on. Here we have the correlation of the concepts. First of all, we have the SAF system. So the proposed integrated IoT healthcare system is named SAF, where the initials for SAF stand for Safe for Animal and Food. So in order to create this system, we studied, analyzed, and compared the optimal approach for the project, but at the same time, we tried to apply eco-friendly and animal-friendly technologies. Here we have a little graphic representation of the system. This is a SAF system. We utilize Internet of Things, we utilize application programming interfaces, and we utilize cloud computing. So all these different concepts exchange information in order to meet a common goal, which is the traceability of sick animals and the monitor of the whole production process. We will see more details about this in the next couple of slides. So starting off with the features and specification of the project, for the main functions we get sensor measurements of 4 different instances, which are the farm, the static location where the animals move, the milk refrigerator, which is the location where the milk is stored, the truck carrying the milk to local markets and so on, and the animals themselves. So we send and store data in the cloud computing service, and we display the latest measurements on developed Android mobile application. So for each of these instances, we monitor different parameters. For the animals, we monitor the temperature, the coordinates as X and Y, the average temperature. For the farm, we monitor the temperature, humidity, and methanium. For the milk refrigerator, where is the milk stored, we monitor the temperature, humidity, the level, the pH index, and the weight. And for the milk carrying the truck, we monitor the temperature, humidity, the tank level, and the coordinates as X and Y. Here we have a graphic representation of the whole system. At the left, we have the sensors and the microcontrollers. So we have the SIP device where we place eco-friendly microcontrollers to the animals. We have the device attached to the farm, we have the device attached to the milk refrigerator, and device attached to the truck carrying the product. So all these different instances send data to an application program interface, which is in brief words API. So we post the data to the cloud using JSON format, and the data is stored in the database on Google Five-based cloud service. And finally, the farmers and the users can fetch the data from the database, and they can display the data in a mobile application. Here we have the layers of the data. It's another presentation of the system. At the bottom layer, we have the sensor measurements, the microcontrollers. Moving up, we have the API. On the next layer, we have the database, the cloud, and finally the Android app. But why is this presentation important? Someone would say, Chris, you already saw as the architecture in the previous slide. This is important because the system is created in such dynamic way that only by changing the bottom layer, which is the sensor measurements and the microcontrollers, we can have a whole new branch system for another use case, which could be fishery management, smart buildings management, and so on. So only by changing this bottom layer, the 4 different layers can adapt, and we can create a new use case simply and without any other modification. Moving on to the variables and intervals, we have 4 different entities as we said before. So for each entity we monitor different variables, temperature, the daily average, location, and so on. And as you can see, the intervals are different for each entity and variable contained in the entity. This is because some variables are more important than others. For example, temperature is of great importance compared to the location, where depending on the season of the year, we might monitor the location more frequently, especially in summer, while in winter we don't want to monitor the location in relative low interval. So for each entity we utilize different technologies. For the animals themselves we utilize LoRa and GPS. We selected the LoRa after comparisons with Sigfox, Zigbee, NB IoT, and other technologies. For the farm we use Wi-Fi and RFID. For the tank we use Wi-Fi and simple Arduino basic components, and for the truck we use GSM and GPS technologies. So to the implementation of the system, and specifically on the application programming interface, someone could ask how the data is being fetched and published to the cloud. So we have the API, which was implemented in the Node.js environment, and it's basically the tool for collecting and storing the data. It acts as the mediator for storing the data in the Firebase NoSQL database. So we create 4 different interfaces in the API, each of them which is unique. We create the farm, the ice bathing tank, the truck, and the animal themselves. So each interface has a unique URL in order to receive the HTTP post requests from the sensors. So when the data is collected, it's being stored in the database and displayed in a JSON format. And moving to the hardware selection, in order to monitor the animals, we use the LoRa TTGo T-Beam device version 1. So the features of this microcontroller are it's a LoRa transceiver module based on the famous ESP32 microcontroller. It has built-in GPS unit and rechargeable batteries. It has integrated Wi-Fi and Bluetooth technologies, and the good thing is that it has a fully programmable board named AXP192, which is responsible for the power supply and management throughout the entire board. So someone could say that we just get a simple microcontroller and everything is solved. The issue with the LoRa technology is that it requires a pair of devices. So if we want to monitor just one animal, we will require 2 of these devices. So going on a large scale, let's say 1,000 animals, we will require 2,000 of these devices, 1,000 acting as the transmitter and 1,000 acting as the receivers. So this, of course, would increase the whole cost of the product. So we thought of creating a peer-to-peer system where this little device can act as a node by changing the states where it operates. So for example, we have node A sending a LoRa packet to node B. Once the node A has transmitted the packet, node B waits in the receive state. Once it receives the packet, it sends a response to node A that, I got a LoRa packet from you, and then node A is going to receive state, and basically this is the dynamicity of the system. All nodes can act as a transmitter and a receiver. So this is the dynamicity, and we have developed a system where we don't require a pair of a transmitter and a receiver, but each device can act both. Moreover, when we can't access a node, a specific node, we look for the predecessor of the success or the successor of this node. So let's say we want to access node C, but node C is out of range, is out of battery, or something else. We look the next closest node to that. So we can get the latest measurement from node F, for example, which is next to the node we try to access. Of course, we have some analytics which are important, and they help us to identify conditions such as illness of animals and so on. So to perform, so we use trajectory analytics. In particular, we use GPS measurements taken at the time interval t in the latitude and longitude pair format. So we use the average velocity v of each farm animal, which is computed by equation 1. We also use some other analytics, but due to shortage of time, we just cover those two, which are the most fundamental ones. We use the temperature humidity index named THI, which is shown in equation 2, and is a major indicator of the farm condition, where T is the farm temperature in Celsius degrees and R is the percentage of relative humidity. We also look for events that can tell us that something is not going right. For each entity we have different events. We look for an animal if it's gonna deviate from the whole herd. We look for unusual temperatures, for large percentages of slow animals. If the herd moves in a not proper way, and we also look for these events, which are for the other three entities. So the project innovations are many. Among the use of new technology and network protocols, which is a Google Firebase, which has been out for 4 or 5 years or something close to that, and the LoRa communication protocol, which was developed in 2015. We offer real-time traceability of animals and objects. This is one of the first peer-to-peer systems that utilize the LoRa technology in the field of agriculture and livestock. The project is highly scalable and highly adaptable, and as we previously presented, the system's architecture is built in such a way that by changing only the bottom layer of the pyramid, we can create a similar system with other application in the smart grid, smart homes, smart buildings, and the smart world. In conclusion, we studied and applied new technologies in the field of agriculture. We used environmentally and animal-friendly technologies. We ensure the product safety and hygiene. We offer an efficient real-time monitoring system of all units for the dairy products. We utilize a cost-effective in terms of development, installation, and maintenance process system. We present an energy-efficient system in terms of energy consumption, as the LoRa batteries may last up to years without any type of recharge. And finally, we present an easy-to-use Android application. So for future work, we want to perform analytics and machine learning at the bottom layer, which is the sensor and measurements. So we want to perform TinyML and TensorFlow Lite. At this point, we perform some analytics, but these are on the top layer, which is a database in the cloud. So in future work, we will try to go to the bottom layer on the sensors and perform machine learning before the data reaches the cloud. Another future direction of this work is the integration of neural networks on Raspberry Pi devices, which will act as the gateways. And we also want to create an automated system for smart energy management, so the system can perform functions on itself based on the requirements. So, for example, in the summer where measurements are more frequent, the device will go less time to sleep, while in the winter it might go more frequent to sleep, and such functions that can create a system that it manages the energy on its own. So that was pretty much it. Thanks for your attention. If you got any questions, I'll be happy to answer. Thank you.